Welcome to the Chapter 10 TCA cycle. Woo! And the crowd goes wild. All right, to start it off, does anybody have questions from Chapter 9 or Chapter 8 or Chapter 7 that relate to biochemistry?
No, but I can't learn without it.
I can't teach with that on.
With
the sheet.
Do it for the snap.
All right. Quick recap of Chapter 9. Glycolysis. So which three reactions are our irreversible reactions?
1, 3, and 10.
1, 3, and 10. And what are those enzyme names?
Hexokinase, phospho, hexo, no, I mean I went down in order. And then the last one has pyruvate in it.
So we got hexokinase, phosphofructokinase 1, and pyruvate kinase. How many NADH do we make with glycolysis? 2. How many ATP net do we make? 2 also. How many CO2 do we make? Yeah, y'all give me that look because it is 0, right? That is correct.
I don't know. 0.
All right.
You tricked us.
Well, what enzyme makes NADH?
Oh, the one with water, dehydrated, glyceraldehyde 3-phosphate dehydrogenase.
Yes, glyceraldehyde 3-phosphate dehydrogenase. So dehydrogenase is a dead giveaway. Good.
We learned.
So we are going to get going on the TCA cycle. Hopefully this is just going to last an hour today so we can get home early and enjoy the weekend. Parker seminars.
Yeah, are we going?
We gotta go.
I know, it's correct for everyone. That was just our try. That we're special.
Everybody has to go on Friday.
All right, so I've got a little bit of a sore throat, so if I'm drinking, it's just water, and it's just quenching it.
Is there whiskey in that water?
No, there is not, unfortunately. All right, TCA cycle. So with glycolysis, our main goal was to produce those 2 ATP and to make pyruvate, right?
Yeah.
So our main goal with TCA cycle is to make reducing agents, such as NADH and FADH2. Right? So those are our main purposes because those reducing equivalents are then going to go over to the electron transport chain, be pumped into the mitochondrial matrix, and then the passing through of that will create ATP, which will keep us alive.
Question that I didn't know the answer to. The first one happened in the cytosol, right?
Yes, glycolysis happens in the cytosol. So TCA cycle and electron transport chain are going to happen within the mitochondria. Good. All right, so we're not quite at the TCA cycle yet. We've got to do acetyl-CoA, so making acetyl-CoA from pyruvate. We talked about this a little bit last chapter. But what's the major molecule that's kind of our go-between between fats, carbs, and proteins? Acetyl-CoA, absolutely right. I think that's going to be on your quiz probably today. Don't forget about the quiz. So, all right, so citric acid cycle is the central pathway for recovering energy from the 3 major metabolic fuels. And that's just because all these 3 can make acetyl-CoA, which then directly goes into the citric acid cycle. So whether we eat carbs, fats, or proteins, we can all go through the TCA cycle to get energy from them. Really what we're trying to do is we're just trying to take the hydrogens off of acetyl-CoA and all the intermediates that we're making and take them elsewhere. So really we're just trying to take hydrogens off. So like we said, glycolysis happens in the cytosol, but the next step happens in the mitochondria. So we got a nice big picture here, kind of going over all the processes. So started off with glycolysis, made pyruvate. Now we're going to use pyruvate dehydrogenase complex to make acetyl-CoA, which will then directly go into the citric acid cycle. So this equation, got to know this equation. Got to know it, got to know it, got to know it. Chemical equation. Good. So the enzyme that catalyzes changing pyruvate into acetyl-CoA is pyruvate dehydrogenation complex. There were at least 3 questions when I took this test just about this enzyme or this reaction in general. So if you don't know it, it's going to be unfortunate. But if you do know it, you're going to be like, thank you, these are great points. So changing pyruvate to acetyl-CoA. Got to know the 5 intermediates. So we've got coenzyme A or CoAsh, NAD+. It does not have the hydrogen on it, so that's a big key. So the coenzyme is NAD+. And we've got TPP, lipoate, FAD. So I just remember the first ones. I try to do the hardest ones first, and I always forget. So I'll try to do TPP, lipoate when I'm trying to go through this in my head. And then you know that with acetyl-CoA, pyruvate doesn't have a CoA on it originally, so it's got to have it at the end. So there's got to be a coenzyme A in there in the middle somewhere, and then NAD, FAD. That's usually how I remember it, or whatever works for you. That's fine, but you got to know those 5. He'll probably ask something along the lines of, which of the following is not a coenzyme for pyruvate dehydrogenase complex? And the answer will probably be, like NADH or FADH2, just because that's a product. So, or a potential product.
And that's just that enzyme turns pyruvate into acetyl-CoA?
Yes, it just turns pyruvate into acetyl-CoA. Also makes CO2. So that's important too. So CO2, so really what it does is it splits this carbon-carbon bond right here. So now acetyl-CoA is just a 2-carbon molecule. So I don't know if that's interesting to y'all or not. Kind of interesting to me. But got to know the enzyme name, got to know the coenzymes, got to know what it starts with and what it makes. So a lot of people think that, oh, it's pyruvate dehydrogenase complex, so it's making pyruvate. It's not. It's dehydrogenating it. Exactly. So if we know our nomenclature, we'll be fine. So this happens within the mitochondria. So this is the first enzyme that's working inside of there. Really, it's kind of a combination of 3 enzymes all working together, but I don't think he's really going to stress the names of all 3 of those. I don't think he did that in class, did he? So really just got to know these 5. So TPP is also thiamine pyrophosphate. I'm pretty sure he's only going to put the letters on the test, but in case he doesn't, got to know the names as well. Thiamine pyrophosphate, flavin, adenine, dinucleotide, coenzyme A, lipoate, nicotinamide, oh my god, I can't even speak today. Nicotinamide, adenine, dinucleotide. So NAD, FAD, TPP, CoAsh, lipoate. All right, so how it works is pyruvate dehydrogenase is going to catalyze the decarboxylation of pyruvate. So that's going to use TPP and make the acetyl group. Then this second enzyme is going to transfer the acetyl group onto CoAsh, making acetyl-CoA. And then the third enzyme is going to regenerate the disulfide to make from lipoate and pass the electrons from FAD to NAD. I don't think he's going to ask you specifically about any of these 3. Don't think, but if he does, I covered it, so it's fine. So, Dr. Sarkar, as I said last time, he really likes to know what regulates and kind of controls these reactions, because that's what kind of makes it functional. So this is how diet can influence these processes in our bodies, or if you have deficiencies due to a congenital disorder or something that you've acquired over the years. It's just really interesting to see how these can be affected by our everyday lives. And so knowing what regulates it and what turns it off, turns it on is really, really important.
The PDC is just that whole equation?
Yeah, so the PDC is just so it's the complex. It's all that, yeah. So the complex it's called complex because there's kind of 3 different enzymes all working together. right? Because it's those.
So we had from that the transbutylase and what besides the enzymes, what else do we need to know from that? Like just to prove that.
No, I would know the coenzymes, know this name,
Okay.
know everything on top, know everything on bottom, know what starts, what finishes.
The pyruvate, not the structure, right?
No, you don't need to know the structure. Cool. So it's inactivated by ATP, NADH, and acetyl-CoA. All right. So who can tell me why those three things would inactivate this enzyme or this complex?
Because once you get enough acetyl-CoA, you're going to stop making it.
Exactly. Because if we have enough of it, why would this enzyme turn on to make more? If we have excess, well, we keep producing excess. That's a waste.
Same with the NADH.
Exactly. So if we have really anything on the right side of this equation, if we've got NADH, if we got acetyl-CoA, or if we got ATP, really, because that's the whole end game of all this overall is to make ATP, right? So if we've got any of those things, this is going to turn off for a little bit until we need NADH, or we need ATP, or we need those things again.
Fatty acids come into play?
I think where do fatty acids come into play? It's enough stored. I guess it's enough stored energy, maybe. So it's activated allosterically by pyruvate, AMP, NAD+, coenzyme A, calcium. Really, so everything on the left side of this equation, if you've got more starting materials, then obviously it's going to drive the equation forward to make pyruvate, to make ATP, etc.
Don't judge me, but I forgot what allosterically means.
Which one of y'all can tell her what allosterically means?
Oh, you don't know?
Y'all got to learn. Y'all can teach yourselves.
I learned it. Oh,
Substrate financing.
Al is different.
Formally different structure.
I thought that was an isomer.
It's an isomer.
Just tell us. We don't know.
Self-learning. Self-learning. Allosterically. Look it up. You got to know what an allosteric inhibitor is. My uncle made me look up vocabulary words like all growing up, and I have never forgotten those words. So if y'all look it up yourselves.
Binding of a protein to a site other than its active site. Oh, yeah.
Cool. So allosterically is binding to a site other than the active site. Good. So like we said, so it's inactivated by really products. It's activated by the things that it's starting with. And it can be regulated by covalent modifications. That's going to be a little bit more permanent, right? A covalent bond, it's the strongest bond that we have. So if we phosphorylate it by a kinase, right? Kinase phosphorylates. So if we put a phosphate on there at all, it's going to inactivate it. And it's also activated by the dephosphorylation of it. So if you take that phosphate off, it's back on, right? Really simple. Put a phosphate on, turns off, take it off, turns back on. Really simple. All right, TCA cycle, citric acid cycle, Krebs cycle, whichever one, it's all the same. Happens in the mitochondria. Happens in the mitochondria. So, like we said, acetyl-CoA is kind of the main intermediate between all these fuel sources. Let's get to the importance of why we're doing this. This pathway is the final common pathway for the oxidation of carbs, fats, and proteins, because all these make acetyl-CoA. It generates reducing agents that act as electron carriers. So NADH and FADH2 are those electron carriers. And it not only provides intermediates as precursors for amino acids, biosynthesis, but also supplies precursors for the synthesis of other important molecules, such as hemoglobin, neurotransmitters, purines, pyrimidine bases for nucleic acids. So we can see it's very involved with, it's got a very global effect on the body. So I think maybe later in try 1 and try 2, like these names will come back up and you'll see them in different places in the body. Like, oh, okay, here's an intermediate from the Krebs cycle being used for a different purpose other than just for its hydrogens or what have you. So the body's very connected. Like we said earlier, it reuses things so it doesn't have to make them again. So really kind of exciting. Involves anaplerotic reactions. Got to know that definition. We'll get to it at the end of the chapter, but when I took the test, he was like, what's the definition of an anaplerotic reaction? And I was like, definitely didn't study that. So I guessed, and unfortunately wrong. But you will not, because I'm telling you that you should know that definition. Like I said, it links with other pathways, and it produces ATP. So 1 molecule of ATP per acetyl-CoA. And actually, it's in the form of GTP, But we will get there. So, like I said, it's all in the mitochondria.
So the ATP is in the form of
Yes. So a GTP is made, which really, it's the same thing. It's the breaking of those phosphate bonds of GTP is the same releasing of energy as ATP, right? It's just guanine instead of adenine.
Oh.
All right, questions before we start?
So, just memorize that. Definition. Will it be verbatim most likely, or not?
It'll probably be, yeah.
Verbatim.
Cool. All right, I like to stay with this page just because it's got everything on it. So really, I don't know, 40% of your test is right on this page. So if you know that, that's pretty exciting.
40.
Roughly 40%, not guaranteed. Yeah, so we said this test is glycolysis, Krebs cycle, and the 2 chapters before that, right? So I don't know exactly what the numbers are going to be, but the majority of the information is going to be coming from glycolysis, Krebs cycle.
You said there shouldn't be too much room for the carbohydrates, which is chapter 8.
Yeah.
Bioenergetic, and then 6 is regulation, like insulin, or the insulin food stuff.
Yeah. So.
Yeah, let's do it.
All right, so we've got our acetyl-CoA. So the very first thing that happens is acetyl-CoA and oxaloacetate are going to combine to make citrate via citrate synthase. So
That's already a lot.
it's already a lot, yeah. So a lot of big words. You'll get it, just like y'all are going to get glycolysis, big words, right? It's not that difficult. So where is oxaloacetate coming from? Well, if we kind of look around the circle, it's kind of the last thing that's made as a part of the Krebs cycle. So really, oxaloacetate is just recycled and starts the cycle all over again. So this is catalyzed by citrate synthase. So whenever you see synthase, it's making something. It's synthesizing something. So it kind of makes sense that citrate or citrate is being made by citrate synthase. The hard part is just remembering what 2 molecules combine to make it. But if you can remember that acetyl-CoA is coming in from the top, and then oxaloacetate is at the very end, swinging around and combining with acetyl-CoA, that's kind of how I try to visually picture this and kind of put things. It's like, oh, it's in the top right, or it's in the bottom right, bottom left, top left, what have you. Definitely don't have a photographic memory. Short-term memory is way too bad for that. But if I see it 30,000 times, then it's definitely ingrained in there. So look at this picture 30,000 times. So that's our first reaction. It's a condensation reaction, which doesn't quite make sense to me off the top of my head because water is being put into it as opposed to being made from it. So I'm not quite sure on that one. But the main, so similar to the glycolysis, similar to glycolysis, we're going to need to know all the enzymes, what's being made, and what was before, what was after. And this one specifically, you really need to know the types of reactions. So when I'm saying condensation or hydration or oxidative decarboxylation, that's huge. We definitely need to know these for sure. So we've got citrate. So the next step, what we're going to do is we're going to turn citrate into isocitrate. All right, we've got this cis aconitase in here. not that big of a deal. He doesn't really care about the intermediates so much. So we're turning citrate into isocitrate, and then overall that is being catalyzed by aconitase, the enzyme aconitase. So all of the enzymes are on the inside of the circle, if you ever get lost in there. So if you want to try to highlight the major products one color, or highlight all the enzymes one color, highlight all the other like GTPs or what have you, a different color, so you can kind of orient yourself, you can absolutely do that. So we're going from citrate, so it makes sense that the next thing that we're making is isocitrate. So if you're ever trying to remember the order, that makes sense that that would follow it. So aconitase is a combination of a hydration, of a dehydration and a hydration reaction. So what we're doing here is we're taking citrate, we're removing a water to make this intermediate structure, and then really we're putting that water back in at a different place to make isocitrate. So isomer, it's pretty much the same thing, just rearranged. It's like what we did with like fructose, glucose and fructose, glucose 6-phosphate and fructose 6-phosphate. We kind of just changed it around a little bit. Same principle. So we are at isocitrate. We have not made anything else besides just those two things here. We haven't produced anything yet. So the next step is where we make our first production of something. So we've got isocitrate being turned into alpha-ketoglutarate. Yes? Yes. All right. So that enzyme is isocitrate dehydrogenase. All right. When we see dehydrogenase, what are we immediately thinking? So when we see a dehydrogenase, we've got 4 of those dehydrogenase enzymes.
I think NADH, but
Yes. So we've got 3 dehydrogenase enzymes. We've got isocitrate, alpha-ketoglutarate, succinate dehydrogenase, and malate dehydrogenase. If you look at where all those arrows go to, everything that is a dehydrogenase is going to make some kind of electron carrier. It's going to make either NADH or FADH. So this first isocitrate dehydrogenase, we see a dehydrogenase, we're thinking NADH or FADH2, right? We're thinking one of those. This first one happens to make NADH. 3 out of the 4 make NADH. Really, it's just memorizing the one that makes FADH2, right? Because that's the one that's different. Do you think he's going to ask you about the one that's different than the other ones? Yeah. Probably. So isocitrate to alpha-ketoglutarate. The words suck. I'm sorry. If I could change it, I'd make it thing 1 to thing 2. But they don't give me that power, unfortunately. So we've made NADH, but we've also released a CO2. All right, so this is a big deal. So we started off with how many carbons? 6 carbons. And now we're down to 5. You don't have to worry about counting it, but this is the first time we lose a carbon.
Is that important?
You definitely need to know that a carbon dioxide is produced here. So this is kind of like our first big step. So we've got NADH made, CO2 made, kind of a big deal. This is an oxidative decarboxylation. So one of the ways, I'm throwing a lot at you right now. I'm sorry, I'm kind of going a little fast. I got a lot going on here. So we've got oxidative decarboxylation. This step and the next step both have oxidative decarboxylation in there. So not only do they make an NADH, but they also release this CO2. So decarboxy, so it's removal of a carboxy C group. So these first isocitrate, and we'll get to, isocitrate dehydrogenase, alpha-ketoglutarate dehydrogenase, both of those release CO2. And when he's asking you, oh, okay, well, what kind of reaction is that? Oh, it's a decarboxylase because it's removing the carboxyl group. So both of those, we lose both of our CO2s in this bottom right-hand half. So whenever he's asking you CO2, in my head I think, all right, CO2, we lose those pretty early on, so that's got to be in the bottom right hand. So we went from citrate to isocitrate to alpha-ketoglutarate to when we get to the next step. So CO2, bottom right hand side.
You don't go. Oh, never mind. Sorry. I was misreading. Okay. No, you're right.
Okay, so to recap, I'll just recap. So citrate plus oxaloacetate makes citrate with what enzyme? Citrate synthase. We make citrate. So then we've got, and that's a condensation reaction. So the next step, we're going to turn citrate into isocitrate, because that only makes sense that citrate and isocitrate would follow each other. And that enzyme is a conatase. Don't have a good way of remembering that. I just remember A, it's early on, or Akon. I don't know. He's like my favorite artist when I was like 8th grade. I really liked him. Anyway, so early on, he's at the top. So then we go down, and we've got isocitrate, turning isocitrate into alpha-ketoglutarate. Since it's an isocitrate dehydrogenase enzyme, dehydrogenase, we're thinking, yes, we know that isocitrate dehydrogenase specifically makes NADH, but whenever we see dehydrogenase in general, we're thinking we're losing some kind of hydrogen. And it's going to attach to an electron carrier, and this one is NAD. All right, so this one we also lose carbon dioxide. So if we're losing carbon dioxide, this type of reaction is going to be a oxidative decarboxylation. Exactly. So now our next step, we're turning alpha-ketoglutarate into succinyl-CoA. So these words are awesome. You'll get them. So alpha-ketoglutarate to succinyl-CoA. This does the same thing. This does the exact same thing. It's an oxidative decarboxylation. Okay? It's a dehydrogenase, right? So if it's a dehydrogenase, what are we going to do? We're going to take a hydrogen off, and it's going to go make an NADH. All right? So there's our second NADH. So it's also losing a carbon dioxide. So overall, this type of reaction would be categorized as what? Oxidative decarboxylation. You're taking off a carboxy group. So in this one, it just happens to put a CoH on to make succinyl-CoA. Not that big of a deal. All right, so we've already got 2 NADH made. We've already made our CO2s. We're not releasing any more CO2s from here on out. So the first half is when the CO2 comes off. So if you're ever trying to think, yeah, so after this, no more CO2 is released. So everything's a 4-carbon molecule up until when acetyl-CoA comes back in to make a 6-carbon molecule. So really the cycle is take off 1 carbon, take off the 2nd carbon, 4-carbon molecule, 4-carbon molecule all the way back until acetyl-CoA comes in, 6 carbons. Come back, lose 1, add 2 more. Lose 1, add 2 more.
Oh, because we're releasing the CoA there.
All right, so y'all tell me, what are the enzymes? In order. Okay, we're gonna snake it. Yeah, so citrate synthase.
Oh God, what? Okay, the first one's
Sec-
citrate, and then it's the iso. No, okay, A1. I can't spell. Oh. She said no.
Aconitase. Isocitrate. Dehydrogenase, yes. Isocitrate dehydrogenase. 4th enzyme that we've done? Alpha-ketoglutarate dehydrogenase complex.
Why is that one a complex?
So this one's a complex for the same reason. It's a complex for the same reason that pyruvate dehydrogenase complex is one, because there's multiple enzymes actually working, and overall that's what happens.
So we only have to know the one now?
Only got another one. Just know the complex. So I'm like word vomiting on y'all right now. it's okay. But if we see anything that says deoxidated decarboxylation, immediately we're thinking, all right, it's in the first half. We're losing a CO2. If we're losing a CO2, that's happening kind of in the bottom right-hand corner of our mental image of the Krebs cycle. So that's either going to be, isocitrate dehydrogenase or alpha-ketoglutarate dehydrogenase enzymes doing that.
So you said the first one was condensation, those two, like 3 and 4 you mentioned, but you didn't say anything about the dehydration and the hydration. Is that important to know that, or you said the intermediate?
So this one's hard to ask for him to say what type of reaction. A condensation is a difficult one to ask what kind of reaction it is because it does both dehydration and hydration. So he can't say, oh, like which of the following. Okay. It's just because there's 2 descriptive terms for it. But yeah. All right. So how many NADH have we made? 2. How many CO2 have we made? 2. Have we made anything else?
No.
Nothing else yet, really? Nothing really of importance. So, no, we put the water back in. So, it's awkward. All right, so now we have succinyl-CoA. The next one we have, so it's succinyl-CoA, and I'm going to jump ahead just a little bit to succinate. So a lot of people get these confused with the order of it, just because they're the same thing. It's not as easy as citrate to isocitrate. So we'll get there. So the first one, succinyl-CoA. So we're turning alpha-ketoglutarate into succinyl-CoA. The enzyme, oh wait, we already did that, didn't we?
Yeah, we're there.
We already did that. So we're at succinyl-CoA. We're turning succinyl-CoA into succinate via succinyl-CoA synthetase. Synthetase. So, synthetase. So this has a T in it, right? Instead of synthase. So up here we had citrate synthase, right? Well, this one has a synthetase in it, that T. So we're making GTP. Right? It's got the T in it, so we're making GTP. That's how I remember it.
Why does it have ATP and ADP in parentheses?
So we're making GTP, guanine triphosphate. It's really the same thing as ATP. Yeah, we can just all we got to do is cleave that phosphate bond, and that's going to release energy.
That's probably important that we do that.
Yes. So this is the only time we make a GTP in the Krebs cycle. So do you think it's important that we got to know the enzyme that does that?
Yeah.
Absolutely, right? So if we're looking at any of these, this is the only enzyme that has synthetase. That's the only one. And it's got those 2 big old T's in it. I guess that second T in it. So you know syntha, it's making an ATP, or it's making a GTP. That's how I remember it. Is that helpful for y'all? Okay. So we've made succinate, and we've made GTP. So now we're at succinate. So we're going from succinate to fumarate. Succinate, fumarate. All right. So in this step, we are making our first FADH2. This is the only FADH2 we make in the Krebs cycle. Do you think that's important?
Maybe.
Do you think he's probably going to ask you which enzyme does that? Yes. So we see a dehydrogenase. So when we see a dehydrogenase, what are we thinking? Some hydrogen's gone, right? Bye-bye hydrogen. So this one, how I remember this one, so succinate dehydrogenase is the only one that makes FADH2. So how I remember this is that it would suck to miss this dehydrogenase as the one doing it. So it would really suck if you forgot which dehydrogenase made FADH2.
Okay. That works.
So All right, so we are at fumarate. All right, so going back, I didn't talk about the type of reaction, number 5, for succinyl-CoA to succinate with succinyl-CoA synthetase. That is a substrate-level phosphorylation. It's the only substrate-level phosphorylation in this entire cycle.
Was that important?
Probably could. He could ask that. Yeah. So if we're phosphorylating something, we're putting a phosphorus on it, right? So this is really the only one where we're taking a phosphate group and putting it somewhere else, right? Because GTP is what we're making. So it would make sense that if we're making GTP, it's got phosphate group on it, that would categorize as phosphorylation. Just really trying to get y'all to see, hey, there's some common sense to this. It's really simple to pick out of an answer choice, right? So if you ask a multiple choice question of which of the following enzymes is a substrate level phosphorylation, you're like, all right, so we're just going down. You say maybe you'll put citrate synthase. You're like, citrate synthase, what does that do? That makes citrate, right? There's really no phosphorus going on there, no. All right, what about isocitrate dehydrogenase? No, that puts a hydrogen, that takes a hydrogen off and makes NADH. So that doesn't have anything to do with phosphorus, right? What about alpha-ketoglutarate dehydrogenase complex? Same thing, right? It only takes a hydrogen off, makes NADH. So then you get to succinyl-CoA synthetase. You're like, oh, well, that makes GTP. That's got a phosphate on it. That's substrate level phosphorylation. That's how I think on tests. Is that kind of how y'all think on tests as well? Mm-hmm. So a lot of these, you can easily just go, if you know the enzyme, if you know the name, if you know the description of it, like what type of reaction it is, you can just mark them off just left and right and just say, oh, that's so easy. It's just, it's this answer, it's this enzyme, it's this enzyme. And it's just really just taking the time to say, all right, this is this type of reaction. Yeah, I like to, so if you can draw this, not the structures, because that would take way too long, but if you can draw the circle, if you can draw the circle and say, all right, we're taking oxaloacetate, combining acetyl-CoA, making citrate. All right, and that's with citrate synthase. Write that out. And then maybe write all right, that's a condensation reaction.
Like when you get the test, like once you had, I guess, like quickly draw the cycle.
If you wanted to, yeah. I think we had people ask last try if they could have a sheet of paper for that, and he said no. But you can write on your test, yeah. But yeah, you can't bring in a cheat sheet. But if I would try if you can just write, like the first couple letters, so you're not wasting your time writing everything out. But that is definitely a strategy, yeah. All right, so we are at, where are we at? We're at fumarate, right? We just made FADH2. What enzyme did that? Succinate dehydrogenase, right? Because it would suck to remember which one made FADH2. So we're at fumarate. Next, we're going to make malate. So if you are the kind of person who likes mnemonics, there are mnemonics out there that's like whatever, like C, I, A. 3, 4, 6, 8. Who do we dehydrogenase? That's awesome. Cool. So if there's mnemonics out there, I encourage you all to look those up. If a quick Google search will do that. I don't have any off the top of my head, but I'm sure classmates have them. So we're going from fumarate to malate. And this is catalyzed by fumarase. So pretty simple. So fumarase is going to break down fumarate, make malate. This is a hydration reaction. So we're putting water in. Like I said, I still don't know why condensation reaction at the top is classified as that when it's doing the same thing, but that's just me. So we are putting water in to make malate. So our last step that we have we've got malate going to make oxaloacetate. And this is a dehydrogenation reaction. So if it's a dehydrogenation reaction or if it's a dehydrogenase, what are we making? An H is released, right? So this one comes down and makes NADH. This is our third NADH that we've made. And we've pretty much reached the end of the Krebs cycle. Right? We did that in like 30 minutes. That's awesome. Let's go back and touch up, right? So we want to like actually keep this in our brains. So one big difference. So we've got four different enzymes that are making either NADH or FADH2. All right, and under those, we've got two categories of those types of reactions. We've got oxidative decarboxylation here, oxidative decarboxylation here for isocitrate and alpha-ketoglutarate dehydrogenases. But over here, for succinate dehydrogenase and malate dehydrogenase, they're just dehydrogenation reactions. So they're making the same thing. Why are they different?
Because they're not making anything else.
Because those two, malate dehydrogenase and succinate dehydrogenase, are only making FADH2 and NADH. The ones down here, alpha-ketoglutarate dehydrogenase, isocitrate dehydrogenase, those are releasing carbon dioxide. So that's where those are different. So that's why there's a difference between oxidative decarboxylation. The release of the CO2 is a marker, and that's really why they're named differently than malate and where am I at? Succinate dehydrogenase. So bottom right of our page, we've got our oxidative decarboxylation. On the left side of our page, we've got just our dehydrogenation.
You're the dance room. The songs are killing me.
Only I told him to put his ghost costume.
All right.
He said no.
So we've got that. That's a big distinction to be made. So let's turn this off. We'll keep it on. So let's go through it. We're going to snake it, starting from the back. So you're going to say the enzyme and the type of reaction it is.
The citrate synthase.
Synthase or synthetase? Synthase. Okay. And what does that make?
It makes citrate.
Pretty simple, right? It's the first thing, right? Start your day off with vitamin C, right? Orange juice in the glass in the morning. So citrate, synthase, it's our first thing.
What is synthase? Does that mean making that?
Yeah, it's like synthesizing it.
So like all the others, they like start with the thing, and then the name is for like what they're coming from, like fumarate goes to fumarase.
Mm-hmm.
But this one's like you have something go through citrate synthase to make citrate.
Yes, so you're right. So the citrate synthase is the only one really in the, yes, it's the only one in the cycle where the enzyme name is describing what's being made. So citrate synthase creating citrate, but all the rest of them, the name, the enzyme is following what's already been made. So we've got isocitrate being broken down to alpha-ketoglutarate by isocitrate dehydrogenase, right? Because the isocitrate is having a hydrogen being removed from it, making something else. Same with alpha-ketoglutarate dehydrogenase making succinyl-CoA because we're taking off a hydrogen from alpha-ketoglutarate. So that's a good distinction to be made.
Back to the snake.
Back to the snake. So we've got citrate. What are we doing after that?
What was the type of reaction? Did you say that?
Condensation.
You know, just make two into one.
Mm-hmm. Yep, so aconitase is going to be both a dehydration and hydration reaction. So it doesn't really make sense, like, well, I mean, it does make sense to rearrange it, but so aconitase, it's really simple, but it gets complicated by the fact that you got to take water out and then put it back in.
I don't even know why we have to, like, why he puts that in there, though.
Yeah.
Because we're taking water out, putting it back in, making cis iconitase, and then, like, really, that's pointless, isn't it?
Well, it's not pointless because if you look, taking water out. So we're taking, where's that water coming off of? We're taking this water off over here. And when we're putting it on, we're putting it on this carbon here. So really, what we've done is we've changed where that hydroxyl group was located at on the molecule, which allows that hydrogen to be more accessible. So by putting it from the middle of the molecule to the end of the molecule, there's less, it's like steric hindrance. So it's just more accessible. It's like taking when you're in the grocery store, you take that thing off the shelf that's right in front of you. You don't like reach to the back. And you're like, okay, I'm gonna take the one from the very back of it. No.
I do that all the time.
And like, it'll last long if I grab from the back.
No, I'm like, people, well, it depends on what it is.
People don't touch it.
All right, so we've made, what did we make again? What did we make again with a conatase?
You're not the snake. I'm sorry.
What are we making?
Yeah, what did a conatase make overall?
No, isocitrate.
Isocitrate, right? So we've got citrate synthase making citrate, a conatase making isocitrate. All right, what is the next enzyme that we've got? Isocitrate dehydrogenase, and what type of reaction is it, and why?
Oxidate carbon.
Mm-hmm.
It's releasing CO2.
Exactly, it's oxidative decarboxylation because it's releasing CO2. What else is important about this enzyme?
Produces NADH.
Exactly, it produces NADH, right? So this is the first time we've made NADH. It's also the first time we've made CO2. So if we've ever seen anything CO2, we're thinking bottom right-hand side of our graph. All right, next enzyme.
Alpha K dehydrogenase.
Sorry.
Bless you. Alpha-ketoglutarate
Yeah.
dehydrogenase.
In my head, it's an alpha K.
All right, and what does that enzyme make?
Because of dehydrogenase, the hydrogen's coming off to form NADH,
Mm-hmm.
and then it's an oxidative decarboxylation in reaction, so you're going to make CO2.
Exactly, and what's the next structure that's made? Succinyl-CoA. Succinyl-CoA. Just trying to get y'all to practice saying this, just because, like if you say it more, you'll kind of understand it.
It's like Spanish.
All right, so we've lost a CO2. We've made another NADH, our second one. It's an oxidative decarboxylation reaction because we released that CO2, and now we've got succinyl-CoA. All right, so our next enzyme is what?
CoA synthetase or whatever, because you're making GTP,
Yes,
and it's a substrate level phosphorylation because of the GTP.
exactly. And how are we going to remember that succinyl-CoA synthetase makes GTP?
T.
It's got that extra T in it, right? Good. And what does that make?
GTP.
The structure. What's the next? Succinyl-CoA. Succinate.
It sucks.
So, good. So, we went from alpha-ketoglutarate to succinyl-CoA, and now we just went from succinyl-CoA to succinate. Succinyl-CoA synthetase because the enzyme is following the molecule, and we're making that GTP, substrate level phosphorylation, because it's with a phosphorus. It's got a phosphate group involved with it. Good. What's the next one? Good. Succinate dehydrogenase. Good. And what's the next overall? What type of reaction is that? Yeah, it's a dehydrogenation reaction. And what are we making? Fumarate. All right. And how are we going to remember this enzyme as opposed differentiating it from succinyl-CoA synthetase? What did I say about succinate dehydrogenase and FADH2? It would really suck if you forgot that succinate dehydrogenase was the only one that made FADH2. All right, so this is really the only dehydrogenase one that we have that makes an FADH2 electron carrier molecule.
It sucks. It's not cool enough for the NADH.
Exactly. So now we're at fumarate. To the back. What are we doing next?
Using fumarate to make malate.
Good. What else is happening there?
Hydration reaction.
Hydration reaction. Anything else really happening? Not really, right? So that one's kind of lame. So like we said, the enzyme fumarase, we're breaking down fumarate. So it's not we're not making fumarate with fumarase. right? The only one that we're making with the same name is citrate with citrate synthase. And all these other ones, we're starting off with what that enzyme is talking about, breaking it down, making the next thing. So we're at malate. What's our next enzyme? All right, we see a dehydrogenase. What are we thinking? We're thinking a dehydrogenation reaction, which means we're doing what? Dehydrogenation. So, yeah, right? So we're taking off that hydrogen, and we're going to make NADH. Exactly. And what are we making after we make from malate? We're turning malate into what? Oxaloacetate, right? And that's the end of the Krebs cycle. And then we come back in, we bring acetyl-CoA back into the picture, combine it with oxaloacetate with what enzyme? Citrate synthase, and we make citrate. Perfect.
I have a question. So you didn't talk about the irreversible steps, but I know he mentioned them in class. Do you test any of those normally or no? The 1, 3, 4.
Are there irreversible ones on this?
Yeah. The ones that only have one arrow, not double arrows. So 1, 3, 4
Mm-hmm.
are irreversible.
Yeah, so reactions, I guess, so citrate synthase, isocitrate dehydrogenase, alpha-ketoglutarate dehydrogenase complex. You can see here that they all have that forward arrow. So those are going to be your irreversible reactions. Yeah, definitely know those three. So in each glycolysis and Krebs cycle, reactions 1 and 3 are your irreversible ones. And then just with glycolysis, number 10 with pyruvate. What is it? Y'all know it. What's enzyme 10 of glycolysis? Pyruvate kinase, right? Pyruvate kinase. And number 4 with this one are going to be your rate limiting enzymes.
So 3, 4,
1, 3, and 4. All right. So what enzyme makes FADH2?
Wait, say what?
Succinate dehydrogenase. All right, so this is how he's going to ask you all the time. That's what he's going to ask you, like which enzyme makes something, and you got to pick it out from the answer choices, or he's going to ask what does this enzyme produce, something along those lines. So if you don't want to go make a test and put wrong answer choices down when you're studying yourself, this is kind of how he's going to ask it. So he's going to go, what enzyme makes FADH2, and y'all are going to yell. Succinate dehydrogenase is going to suck if you remember that this is the only dehydrogenase that doesn't do it. So if y'all know it, if y'all just know it like that simply, this test is going to be a breeze because you're going to be able to pick everything out and just say, that makes that, this makes that, this produces this. You're just going to fly through it. So what 3 enzymes produce NADH? And malate dehydrogenase, right? So we've got isocitrate dehydrogenase, alpha-ketoglutarate dehydrogenase, malate dehydrogenase. So if you see a dehydrogenase, you're probably going to produce some kind of NADH or FADH2. What type of